this computer and we'll get going. All right. So today and tonight, it's going to be kind of fun. We're going to be talking about glacials and glacial landforms and a quick intro into the atmosphere. If you happen to go to Yosemite, before they start requiring permits again, which is in May, I think, the end of May, you can sneak up on there and see some of these glacial landforms for yourself. Otherwise, in the summertime, you have to put in like a month in advance to be able to get a gate pass to go in. But anyways, we're going to be talking about glacials and glacial landforms, and then just a quick little introduction to the atmosphere. So next week when you come to class, I'm going to ask you to bring a few silly little items to have with you next to your computer so we can do some small experiments. All right. And they're easy to get. It's like a plastic bottle. All right. I mean, it's not hard stuff to find. So a couple of things. All right. First thing, we'll talk about the final project intro. We'll do some geo news, some glacier formations stuff, Valley Glacier landforms, which is some group Google Earth practice, and then that atmospheric intro like I was telling you about. All right. And so for next week, some of those things that you're going to need, like basically just 2 textbooks, not to read, but to use as a platform, and then a flat piece of printer paper, and then some 2-liter or any size soda bottles or small ball of paper that you can wad up with a piece of paper. So that's kind of what we're going to be looking at. And I lied. I'm going to do the geo news first, and then I'm going to do the just a quick introduction to the final project. So tomorrow, Sunday, we might get little whiffs of rain here and there, probably not much, but Sunday is looking pretty good to have, 1/10 of an inch, 1/4 of an inch. It could be a little thunderstormy and hit and miss. So some places could get 1/4 to a 1/2 inch. Some places might not get that much, but there will be some extra snow in the Sierras from this, which is really good. And it's the first time we've had rain in like 38 days or something like that. And so you can kind of see here the drought monitor, how it shifted from November 10th to this was yesterday's April 20th. Came out yesterday, April 20th, just to be able to see the change in the comparison of how much of California has gone into the drought. And maybe you saw the governor announced, oh, we're in a drought situation now for 2 of the counties in like Sonoma and Mendocino County, I think. But it's going to be coming very quickly for the rest of us. So just like we've been talking about since the beginning. And why is that important? Well, I just also wanted to show you, this is the snow water equivalencies of percent of average in the northern Sierras, the central Sierras, and the southern Sierras. And basically we're at 29%, 37%, and 17% of what we normally have for this time of year. So it's really bad. And remember last week, a good chunk of all that water in California comes from melted Sierra snow and then gets pumped down to Southern California. So when we don't have the water, not only do our farms and our cities and other things falter with wells falter, but also Southern California folks have some issues. And then there's environmental ramifications of not getting flows in the water in the river. So just things to think about. In the olden days, right, we had droughts, but the rivers would still flow because there was so much groundwater from the wet years and wet times that it would be a gaining stream and flow into the streams. And there wouldn't be too much of a time where the rivers actually went dry, we don't think. So just something to think about as we move forward with this geo news. All right, so kind of changing quick subjects here. This final project information, it's basically going to be the thing that we do the last day of class. All right, so that's kind of our final. I'm not going to be teaching or lecturing or doing anything like that, but you guys are just going to make a 5-stop Google Earth tour. All right, so basically what that means is how you've been playing around with Google Earth all year and some of our Jamboards and things like that. You are basically just going to put 5 different pins on the map that tell a story. All right, so you're going to create a Google Earth tour that lets a hypothetical class of 6th graders discover a bit of Earth science, something that you've learned about. All right, and I know not all of you are going to be teachers, but that's okay. We're going to keep our audience kind of at the 6th grade general public audience. And this is something then that if you can't remember or think of anything that is like a great story, maybe it's someplace that you want to visit and want to go and you want to learn a little bit about the geoscience in that area. But here's the gist, all right? And in Canvas, there is a link to this, but this is kind of, it looks a little overwhelming, right? Like there's a lot of stuff on here, things like that. A lot of this is just tips and tricks. It's not like the whole entire instructions of everything. So here's the main thing. And then I will show you also, which I think is the most important part, the little rubric here. So the rubric is pretty easy. All right. And basically, how about I'll just show you the rubric first to show you what you need to get to meet all the expectations. So basically your Google Earth tour is going to need to have an introduction slide, and I'm going to I have a small video that I've made that I'm going to put up and play for you guys to watch on your own on how to do that. It's like a little tutorial. It takes about 7 or 8 minutes, but it's pretty simple. All right. And so you're going to be able to then just create a kind of a title slide, and then the big meat and the potatoes of everything is just a quick, and when I say quick, I mean 200 words max, which is like 2 paragraphs maximum. All right. I'm not looking for a dissertation or anything like that. I'm just looking for something that quickly shows how you've put your thinking into it and what you've done. But basically, it's an explanation of how students will record their thinking. So like we use Jamboards, we used like Google Slides. I had you guys do your sketch notes and things like that. So if you were to create this, how in a hypothetical class or even out in the public, what types of ways would you have students or the people doing that record their thinking? All right. It needs to have 5 stops, and each stop needs to have some content. So that means when you click on the button, the link, something pops up and it either can tell them about it or it gives them an investigation. All right. And then within that place marker, it needs to have what we call an NGSS doing. So NGSS is the new next generation science standards for those of you that are going to be teaching. And basically what I've been trying to model in this class, I know I've told you some things, but I've been trying to let you investigate a lot of stuff, right? You're doing a lot of things. It's interactive, it's engaging for the most part, as much as it can be. But that's what the NGSS is basically about. And so if you go back over to these, let me zoom in here, sorry. So if you go back into these instructions here, when it says it must contain a doing, I've listed like the 3 or 4 things that I would maybe want to have you include, or the easiest thing. So basically, you could have students asking questions about a spot. So if you flew into like a 3D photosphere or something, what do you want them to notice and wonder about that area? Or maybe you want them to analyze and interpret data, which means data can be a lot of different things. It can be, straight up numbers off a chart, or maybe it's the type of rock they're seeing, something like that, right? So how do they know it's basalt, or how do they know it's granite? Something like that. So what type of rock is this, or what type of river feature is this, and what does that tell us? So those are the types of things that I'm talking about when you say analyze and interpret data. You can have them develop or use models, so sketches or drawing, things like that. And then if you need some examples of sentence starters or question starters, these are some really good questions that you could add, regarding your specific spot. Okay, so that's how this is kind of, when it says NGSS doing, that's all it's looking for, is making sure that you're asking a question, that they're doing something or designing or sketching. And it's not just oh, here's Yosemite. These are the waterfalls. They're really tall, right? You want them to discover something about it without you telling them about it, if that makes sense. All right. And hopefully we've gotten enough practice in this class through my modeling that I think I hope it's understandable. Oops, shucks. All right. And so then another thing is it links or there are links provided to other learning resources where appropriate. So, think of you as a student. Everything that I've given you in this class this semester, if there's something I wanted you to look up or research or think about, I've provided you the links, and for the most part haven't said just go do a Google search, because then you don't really know if that's what I'm asking for, right? So if you want to give your students something to think about and drive on to in terms of discovery, maybe you should provide them that link and make sure it's like an appropriate link where it gives them the information they need in an easy way that's not written at a college level or something like that. Or maybe it's a quick little YouTube clip of a phenomenon or a landslide or something like that, you know? So when you need links, go ahead and provide the link. Not every single one of the stops will need one of those, but if you do need it, that's there. And then the presentation. So here's the last bit, right? So the presentation can be one of two things. It can either be recorded and you have a 5-minute length total, so it can't be longer than 5 minutes, all right? No longer than 5 minutes, short and sweet. And it can either be recorded or given as a live presentation. So like if you go to a conference, sometimes you have prepared slides and you'll present it live, or just like I'm doing right now, presenting it live. Well, maybe I'm not presenting it live. Maybe this is all just a recording and you guys don't know. But you can present it live, all right? And that's the big thing that we're going to be doing. We're going to get into small breakouts. Most likely, we won't have a chance to see everybody's as a class, but within your groups, everybody's going to be presenting, and we're going to be using this what we call tag feedback, which is you're going to leave a sticky note basically that says something you liked about the person's presentation, a question you have about their presentation, and then you're going to give a positive suggestion. So there are lots of sentence starters and things like that over here, but it's just a way to help improve and take feedback. And so I've tried to take feedback after every class by doing the sunshines and blues, right? It's how I get better. And that's how I want to encourage, especially folks that are going to be teaching, to be able to have communication with each other. And you know, sometimes even constructive criticism is a little bit hard and you guys are putting yourselves out there. But when you follow these instructions like this, it's a really positive experience. And I will say last semester, it went really, really well for the class and was pretty fun. And it gives you something to think about. Oh, next time I'm going to tweak this, I'm going to tweak that. And remember, this is meant to be fun and engaging, and we're learning, you know, it's pretty easy to check off the boxes on the rubric, and we can learn and apply and make it better as we go on. But I'm not expecting, you know, like this is a publisher based curriculum or something that it's the most perfect thing right off the bat. That's not what I'm expecting. So this is not something I want you to stress out about or freak out about. It's tell a cool story about something you learned about in this class, geoscience. So some of the things in terms of topics that you might want to think about would be something along the lines of knowing that story you want the virtual field trip to tell. So you want them to discover a great story, right? So you want them to discover it. Maybe each place mark that they go to builds and helps tell a story. Kind of like when we did the landslides, how you were building a story of all the different types of hazards that you were seeing there. All right. Maybe you want to talk about Yosemite and the glaciation, or rivers in Yosemite, or rivers in California, or whatever. There's anything that we've talked about in our class. That's what you can think about. I mean, we've covered geologic time and rocks and their stories, the patterns of plate tectonics, volcanoes, earthquakes, weathering, all that stuff. It can be any one of those topics, and it doesn't have to be US or California centric or even Turlock centric or anything like that. It can be worldwide. If there's different things you see around the world that can tell a story to bring it together, go for it. But so these are just some examples that I've given you. You don't have to use them, but there's cool, amazing geologic stories in California state parks. And this link, I think here, will actually take you to the geoscience. That's the maps that will show you where all of the state parks are in California. If you haven't ever seen where all the state parks are, there's a ton. So, you know, maybe you want to help folks discover something closer to home now that COVID's kind of starting to wind down. Where can they go safely to recreate and still see some good things? So that's what we're looking at right there. All right. It's pretty fun. It's due on that last class. There's no lecture or anything. And this is the thing that takes the place of the final. And I'll be here over the next 4 weeks. If you have questions after I upload the tutorial and stuff like that, you can always ask me. I'll be more frequent about checking my emails and things like that. The Canvas one is the best way to get a hold of me, is that Canvas conversation. And then, you know, we can just, whatever questions you have, I'm here for you. All right. So I just want you guys to know that and have fun. So, whew, you guys okay? I hope, I mean, I don't want to add extra stress to your life. That's not what I'm trying to do here by any means. I want to add something that's a useful skill so that when you get into the credentialing programs, when you start student teaching and things like this is something you'll be able to pull out of your back pocket. And I mean, maybe if you like it enough, you could use it in a class, but at least you'll be able to have Google Earth and give kids a sense of place when you're going in and talking about something. You can fly in and show them, right? So that's what well, not cool, but that's what technologically advanced teachers can do. So anyways, so that's what we'll be doing. We'll in a couple weeks from now, 4 weeks, right? I mean, goodness gracious, we're almost there. So switching gears, all right. Tonight, we're going to talk about glaciers and how they can shape, how they shape the present, or how glaciers shape the present, and what can they tell us about the past in order to predict the future. So that's kind of a mind-bending thing, but that's what we're going to be looking at. And kind of the big question tonight too is, based on the time in our glacier simulators that we're going to be doing, I'd like you to make a prediction about, citing evidence from these simulators, if we'll see California's glaciers grow or sink over the next 100 years. And then, provide a sentence or two explaining your reasoning. And then you might want to check out the California Glaciers Wikipedia page and compare that to like the glaciers in Mount Shasta versus the Sierra and things like that. Because there are glaciers in California. There are a few. Not as big as they used to be at one point. I'll tell you that much, especially during the Ice Age. So we're going to look at some of the general definition of glaciers tonight, ice sheets, alpine glaciers, some general diagrams of what an alpine glacier or alpine or valley glacier looks like, and then the cool things they make on the landscape. And so when you go into Yosemite, these are the things you'll be able to recognize and go, oh, or not even Yosemite, but anywhere in the Sierra, these are the things you'll be able to recognize and point out. I'm like, oh, I remember I learned about this in class. So it's pretty cool. It's pretty amazing. And there was just a brand new paper out about glaciers too. And one thing I'll show you later on as we get out, just came out last week, that is kind of mind blowing. So it has to do with glaciers. Okay, so let me do this really fast, and then we'll get into our first Jamboard where you guys will have some fun time playing with a simulator here. So if you don't know what a glacier is, if you've never seen a glacier or never had the privilege to go stand on a glacier or next to a big glacier, this is what they are. They're just large moving masses of ice. But here's the thing, they're on land, right? If it's on the ocean, that's sea ice, right? The ocean will freeze over, that creates sea ice. That's not a glacier, that's just sea ice. Glaciers are big chunks of moving ice that originate on land. Now, some glaciers will flow off the land into the ocean and then eventually will break off and calve and make icebergs and things, but they started on land, all right? And so just to kind of put the basics in the back of your brain here, in order to make a big moving river of ice, you need to have more snow falls each year so that it accumulates and packs down than the amount of snow that melts each year. So usually glaciers form in really cold places. So places that are really high up in the mountains or really far north in latitude, like Alaska or Greenland or Iceland and places like that, where they don't have enough sun in the summertime to really get too hot to melt things, all right? Or the angle of the sun is not quite high enough. So that's kind of the basics, right? You need more snow to pile up over time than melts. And then you get this big pile of ice and it starts moving downhill, just like everything wants to flow downhill. So here's a cool little glacier flow time lapse right here. Let me see here. I'm not going to play the whole entire thing, but you get the idea. And there's no sound, but I'll better share my sound anyways. There's a little bit, but this is a time lapse.
Time-lapse camera shows that Nigod's Brain's surface ice travels at around 275 meters per year, carving away the rock as it goes.
So 275 meters is what, about a half a lap, or 3/4 of a lap around a high school track, right? Or if you're running around a track. So some glaciers move pretty slow. Some of them move a lot faster than that. But it shows, even though it doesn't look like they move much on a daily basis, eventually they do move quite a bit. I don't know why I get watch ads. I don't wear watches. All right, so like I said earlier, more snow falls than melts in a season. This results in more and more snow that piles up. And then what happens over time, and I love this model. This is from Alaska when I went a few years ago in one of the museums there. They made this really cool glacier model out of glass beads, cotton balls, and a shower loofah, where the loofah is like snowflakes. The cotton balls represent an intermediary stage called firn, F-I-R-N, and then this is called glacier ice. So basically, as that weight of the snow gets so deep, or the snow gets so deep, the weight of that snow pushes down on the bottom and starts compressing those snowflakes and recrystallizing them and turns them into solid, thick glacial ice. But there can be, and this is really important for climate stuff in the next couple of weeks, there's still pockets of air trapped inside of that solid glacier ice. And this is what we can drill into and suck out and melt, I guess you could say, and get the air out. And we can actually measure what the atmosphere was over 500,000 years ago based on 500,000-year-old air trapped in the bubbles of glaciers, which is pretty amazing, awesome stuff. So here is our first simulation, all right? So basically what's going to happen is we're going to open this simulator right here, and I'll put that in the link in just a minute. So what's kind of crazy, what's kind of fun is this is a browser compatible version. So what this means, I don't think people with iPads, this one will work. We'll see. Oh yeah, it says right here, this is not compatible with iPads. But the way this might work is maybe somebody in your group could probably want to share your screen once it happens. And you'll see it's taking a few seconds to load. So give it a few minutes here, not a minute, but just give it a second. It's starting, it's starting, it's starting. All right, graphic system initializing, all that other stuff. So you're seeing it just takes a minute to load. Be patient with it. All right. And it brings up this cool little thing right here. It's this nice, fun little simulator. I don't think it can get really much bigger screen than this or not. It just basically stays this side. But you'll see here, there's a funny looking bear. And if you drag the bear, it basically drags it down into lower elevations where it's greener. So you can see how things change. That's basically how you change your view. Okay. There are some other interesting things. It says, I would like you to click on the advanced tab. So if you go back to our simulator, click on the advanced tab like this. All right. And then it says basically click on the choices in the view box and play around and adjust those sliders. So where you see the view box, which is right down, let me get my little pointer thingy here. Sorry. There it is. So you can see right in here, you can choose what units that you want, but there's lots of things that you can put on here. There's temperatures that you can slide and change. There are average snowfalls that you can change. So like more snow in a year or less snow in a year. You can click on different things and add those. And basically what you're going to be doing is, let me get into the, oops, that's the wrong one. Doggone it. Let me get you the link here in a moment. There we go. Here's the Jamboard. All right. I need some elevator music here while I do this. There you go. That's the right Jamboard. So this is the right Jamboard. Once you get this one, it tells you kind of the instructions on the top. And basically it's asking you for some general notices and wonders. And then in the blue tabs over there, it says, what are some conditions that allow glaciers to grow? And what are some conditions where the glacier retreats? So you can click on different parts of those things and hover over them, and it'll kind of tell you sometimes what they are. You have a toolbox, which is kind of funny. You have a thermometer, and if you take the thermometer, you can go over the top and bottom of the glacier, and it'll tell you different temperatures at the top. Let's see here. We have basically this is a little meter. So what it tells you is how much snow is falling. And ablation means how much is melting away or evaporating or leaving the system through a couple of different processes. All right, that's what ablation means. So in this case, you can see if accumulation is bigger than ablation, maybe we'll start getting some glaciers. All right. You can put little flags on there to see how they travel and how they flow. You can take drills and drill into there and see how things change as they drill over time. It's kind of an interesting thing to see. All right. And just play around with it, see what those do. All right. So I'm going to give you 15 minutes in your group. I will get this link here for everybody for this and put that in the chat as well. And oops, let me see here. There we go. And so we'll give you about 15 minutes here to just play around. What do you notice? What do you wonder? What are the conditions needed for the glacier to grow, for the glacier to shrink, things like that. Oh, and the last thing I forgot to tell you is down here at the bottom is your time count right down there. So you can basically see how many years have elapsed. You can make it go fast or slow. And if you want graphs, you can actually turn graphs on and off over here to see how things have changed over time. All right. So I'll get you into breakout rooms and have some fun. This is a fun little one, I think. And you can all play on your own if you want, or you can have somebody share the screen and somebody record. It's up to you guys. All right. So breakout rooms, let's see here. There we go. Ooh, 5 ought to be good. And create options, 15 minutes is good. And have some fun. All right, welcome back. Good job, everybody. So let me see here. We've been watching you and trying to manage some family fun too. So, all right, let me see here. Share screen. That's what I want. Okay, so here's the good stuff, right? So you guys went through, you saw a lot of amazing things here. Basically had to do a lot with looking at temperature decreasing, maybe cause glaciers to grow, causes the glaciers to get bigger and things like that. Notice the glacier's accumulation closest to the mountain is higher. All right, and then they had some ablation at different rates too. And so these are some really great ideas that you guys are seeing there. Let's see here. So were there any big ideas that stood out to everyone, like some ahas that were like, oh, this is really important. This is something I didn't expect. Nothing. It went exactly as planned. All my glaciologists.
One thing that we saw that was kind of weird was like when the sea breeze temperature was up,
Oh,
and the snowfall was up, it's still like the thickness of the glacier increased, but it was still retreating.
So it got thicker but retreated.
Yeah.
Interesting. All right. And these glaciers are super complex systems, right? And so that was pretty cool. So good observation. All right, and let's see here. See if there are some other big ideas that y'all shared. And the glacier retreated, the ice thickness at the top increased. All right, so I think that's very similar to what we were saying. Let's see here, the temp is lower, the glaciers grow. That's definitely one way, or when there's more snow is another way. When using the drill, we noticed that the glacier was tilting. Oh yeah, so right, the glaciers aren't flat. They're going to kind of flow downhill, and maybe I think what they maybe meant to. So either the glacier is tilted, or also after you drill the hole, the drill holes start bending and tilting and going like that. And this is a really cool thing to notice that was there. And the reason for that is because the glacier actually moves at different speeds. It moves faster up at the surface than it does down at the bottom. And it kind of makes the middle of the ice act like a plastic, almost like silly putty. It's a solid, it's frozen, but it makes it behave in sort of a plastic way where it deforms. Like if you were to drill a hole in the glacier, this is what that hole would do over a few years' time after it starts moving down the mountain, which is a pretty amazing and kind of cool thing. So let me ask you this. Did I already say it? I don't remember, but why do you think it would move slower along the surface of the rocks and the mountains here versus higher up on the thickness of this glacier? What would cause it to maybe be slower? And so let's see here. This is like 800 feet thick. So 800 feet thick is what, 10 stories tall or something like that? No, that'd be 100 feet. It'd be like 80 stories tall. So what would cause things to slow down here? If you, let's say you had to slide down a mountain on a cardboard, what's gonna slow you down? What's the big F word that's gonna slow you down? Think of physics. Yeah, friction, you got it. So the rocks right here have a lot of friction on them. And even though ice is fairly smooth, that friction from all those rocks on the surface are going to cause things to slow down. And so that's why the bottoms of the glaciers actually move a little bit slower than the tops of the glaciers. And there's some really amazing physics involved in glaciology and trying to figure all this stuff out. But if you're interested, you can take some more of those advanced geomorphology classes and things like that. And somebody said also maybe the sun is melting the top layer and making it go a little bit faster too. So yeah, so sometimes the sun maybe could be melting some of it depending on where they're at, and that might change some of the velocities as well, right? And some of the behaviors. So cool, good ideas. All right. Awesome job, everybody. So hopefully you had some fun with that, and it's pretty fun if you do become a classroom teacher. These are fun little, you can go on like the introduction version and let kids play around and poke around and see what they notice, right? So, all right, I know what I forgot to mention. There's that equilibrium line here. And basically that equilibrium line means everything on, well, let me go back over here. Whoop. Everything on the left side of that equilibrium line means it's gaining snow and ice, and everything on the right side means it's eventually losing snow and ice. So it's losing more than it's gaining here. So it's kind of going away on that side, it's gaining on this side, and this is that middle line where it's perfectly balanced, where it's neither gaining nor losing, it's just staying the same. But you see that line of equilibrium can change, right, depending on temperature and things like that. And that's what we're experiencing in today's world. We're seeing a big shift in a lot of these glacial equilibriums here. And so I have a kind of an interesting, fun little, whoops, doggone it. Let me get this. It's a Friday. This one's a rough one for me here. But let me get my link. This is the one I want right here. This link. All right. And so this is what I'm trying to show here. Maybe it's not going to get bigger, but what this is kind of neat and what's kind of cool to be able to see here is that these are the glaciers. It's still moving forward, but you can see over time, it started out way over here, but over time, it starts melting and receding backwards. So the glacier is still moving forward, but it's retreating because there's just not as much ice as there was when it started several years prior to that. So that's one of the cool things that I wanted to show you. And you'll get to explore some of that on your own in just a few moments too. All right. So when we talk about how does a glacier melt then, or how does it ablate and go away? Well, here's a few ways.
The sheet of ice that covers Greenland contains enough frozen water to raise oceans by 25 feet across the globe. As the planet warms, glaciers melt, causing sea levels to rise. But not all of that melt happens at the surface. In the summertime, rivers and pools of meltwater find their way down through the glacier to the bed below. From there, the water runs beneath the glacier until it reaches the ocean. Because meltwater contains no salt, it weighs less than ocean water and rises up the front of the glacier in what scientists call a plume. Around Greenland, oceans are cold and fresh near the surface and warm and salty at depth. As the plume rises, it draws in the warm, salty water, melting the glacier face from the bottom up. Eventually, a piece of the glacier breaks off, making an iceberg in a process known as calving. As the oceans warm, calving speeds up, causing glaciers to retreat and flow faster. Faster glaciers dump more ice into the oceans and drive sea levels higher across the globe.
So it's kind of a crazy feedback loop that we'll be looking at a little bit more in detail with just how much these glaciers have changed in different parts of the world as we get into climatology and stuff. But so here's the big question, right? Why then do we care about glaciers? Why are they important to us? And for the most part, sorry here, chat. For the most part, glaciers play a huge role in California's history here. If you take a look at this picture over on the right, let me get my little pointer again. Right over here, notice that these are old shorelines that they're drawing. And so this one says 8.3 Ka. So if you remember from the first week of school, the first week of class that we had, K stands for kilo, so thousands of years. So between 8,500 years ago, basically, right here, it says sea level was about 18 meters lower than it is today. Okay. 10,000 years ago, sea level was almost 37 meters lower than it is today. If you were to stand out kind of in San Francisco, where we are today, 18,000 years ago, the ocean was 100 meters less deep, right? Or so there was, it was shallower, let's see, shallower, yeah, 110 meters shallower, I guess would be the proper way of saying it. So what that did is as there were lots of glaciers on the land around California, in the Sierras, in the northern hemisphere, and in some parts of the southern hemisphere, Antarctica, as we had these ice ages and glaciers started getting thicker and bigger over time, that water had to come from somewhere. And where it had to come from was these oceans, right? And so as that water got locked up in those ice caps, sea levels actually started to sink. And so during the ice ages, all of this area out by the Farallon Islands and all that other kind of stuff, that would have been, you would have been able to walk out there, close to 18,000 years ago. And that's how we find like mastodon and mammoth fossils and things out there, is because that used to be connected. But now that the ice ages ended, sea levels started coming up, and now it's flooded everything. But that's one reason glaciers were important to us, right? They were kind of that storage bank of fresh water. They're really important these days because they have a big influence on global weather patterns and climate patterns over years and years and years. They play a big role in ocean currents that we'll be talking about in a week or two. And so when the global climate is colder, more fresh water stored up high, which makes sea levels go down. So think about it, as the water evaporates off the ocean and then snows and rains and things like that, if it's staying frozen on the continents without running off, it's going to get thicker and thicker and thicker over time. And then when our climate warms, there's going to be less fresh water because that was trapped as ice. It's going to melt, it's going to flow out, and that's going to eventually cause the sea levels to rise. So one big thing I want you to just think about right now, though, is melting glaciers and continental ice sheets. These are the things when they melt that cause the sea level to rise. If you have sea ice, so ice that forms in the ocean and then melts in the ocean, it does not cause the level of the water to rise or fall at all. And you can do that experiment at home. Just go put some ice in a glass, right? And see what happens when it melts. See if your water overflows your glass after it's all the way done melting, and it won't. But that's just something a seed I want to plant in your head for right now, for later on. Okay. So remember, for us, the reason that they're really important for us too is there's lots of glacier-fed rivers that brought most of those sediments that we've been talking about over the last few weeks into the Central Valley during the past 750,000 years. And speaking of soils in the Central Valley, Dr. Asmarit Bure, who is at UC Merced, kind of an acquaintance of ours, she was just appointed by the Biden administration to take over the complete federal office of science. I can't remember the official name of it, but how cool is that? Soil scientist from UC Merced that studies all these cool soils and the carbon capturing of them. She's now going to be one of the lead scientists in the entire country, which is pretty awesome. So for us, over the last 750,000 years or so, this is where our soils came from. We're from being eroded, glaciers eroding the rocks in the Sierras and depositing those, bring the melt water from those coming out to the valley and being deposited. And so some of the glaciers in historical context here, right, is we know that about 15,000 years ago, 30% of the Earth was covered by glaciers. And that's what we know as a glaciation, or colloquially known as an ice age. So what are some evidence, do you think, that might help us figure out where glaciers were? And that's what we're going to be looking at here in just a minute. All right. So this is kind of what it looked like. If you were to stand on Earth about 15,000 years ago, this is what it would have been. So in order to figure out that evidence, here's what we're going to do. We're going to take a look at the two major types of glaciers: the ice sheets, which are continental glaciers. They cover big, massive areas of land. And then things called alpine glaciers, which are much smaller, and what we'll find in like Yosemite and Glacier National Park and things like that, up in the mountains, basically. All right. So ice sheets are continental glaciers. They basically cover huge areas. They currently cover about 10% of the Earth's surface. And this is a picture of Antarctica. I should probably get a few newer ones here, but I like this one because most people think of Antarctica as just a big flat piece of ice. There are big mountains in Antarctica, and there's submarine or subglacial rivers and subglacial lakes and stuff like that. But it's pretty amazing to think that there are miles and miles thick of ice in some of these areas in Antarctica. And now with modern science, they can do all sorts of cool seismic reflection. So basically using the same science that earthquake scientists use, and they can look and see what the glacier is like underneath, and they can figure out where there's mountains and where there's valleys, and they can kind of get a three-dimensional picture of what parts of Antarctica and Greenland look like underneath the ice, and that'll help them predict how they will melt and behave in the future. And if you were to pop the ice off of Antarctica, there's tons of subglacial lakes and rivers and all sorts of things that are flowing out into the Arctic Ocean, or the Antarctic Ocean, I should say, from these glaciers as parts of a melt during the summertime and stuff. It's a pretty amazing, awesome place. And there's one lake in that a team of Russian scientists last year, 2 years ago, drilled all the way down through, and they think this lake has been covered by ice for over 500,000 years. And they took a sample of that water, but I don't know the results of that yet. I don't know what they found. So they're trying to study and figure this out because some of the moons of Jupiter, like Europa, they have ice covered, basically the moons are ice covered, and they think they have liquid oceans underneath. So if we can get technology corrected here to do that and learn about what's underneath our lakes here under the ice, maybe we can send something over to another planet and maybe find something there. So that's the idea with that. All right, so here's something to think about. 80% of Greenland is covered by ice. It's about 1,500 meters thick, which is almost a mile. All right. Antarctic ice is about 2.5 miles thick, 4,300 meters at its thickest, which is just seems kind of crazy to think about. And of all the ice in the world, Antarctica has about 80% of it. All right. And so here is how this has been going.
Using the most advanced Earth-observing laser instrument NASA has ever flown in space, scientists have made precise, detailed measurements of how the elevation of ice sheets in Greenland and Antarctica have changed over 16 years.
We can actually see some processes at a scale that's almost long enough to tell us about the climate in those two places.
Scientists took ice sheet elevation measurements from 2003, overlaid data from 2019, and analyzed where the data sets intersected in order to see where ice was lost or gained. For example, the study definitively shows that the East Antarctic ice sheet, the largest of all the ice sheets, is growing.
But more importantly, what we find is that growing is more than offset by increased losses coming from the West Antarctic ice sheet, which is thinning very rapidly as it responds to warmer ocean temperatures, specifically in the Amundsen Sea embayment area.
The West Antarctic side, we're seeing strong thinning on the ice shelves, which is causing drawdown on the inland ice, on the grounded ice upstream. Most of that is being caused because of changes in ocean heat flux underneath the ice shelves, which is causing them to thin, and then consequently the buttressing force is being lost again.
So what that means, what she's trying to say is as the front end melts, there's not as much ice to basically hold the glaciers up on the mountains anymore. And so it starts flowing rapidly. It's like kind of kicking out the blocks from underneath a motorhome or something like that, right? You have it kind of wedged in place, and if you take some of that wedge out, it's going to start rolling and going faster. And so that's what's happened in Antarctica.
The grounded ice, and the grounded ice is then flowing faster into the ocean and causing sea level rise. In Greenland, we're seeing different signatures. Again, in the center of the ice sheet in the plateau, we're seeing increased accumulation. So there is a slight increase in mass in the center, but the overall signal for Greenland is one of thinning, and that is being caused by ocean and atmospheric signals acting all around the edges of Greenland.
So we're seeing 200 gigatons per year of ice flowing into the oceans, which is enough to raise sea level by about 2/3 of a millimeter per year.
Combine that with the almost 118 gigatons lost in Antarctica, and sea level has risen a total of 14 millimeters over the 16-year period due to ice sheet melt. It may seem small, but the small changes add up.
What we expect by the end of the century is, on the order of 2, 3, maybe 4 feet of sea level rise. And because we have all of our infrastructure that is built around the coasts, we have a lot of vulnerability to a meter change in sea level rise.
So we'll talk about that going on, but that's a little next week. That's what I meant to say. But the idea here is the ice sheets, that's how they look. We can use modern science to track it every single day. It's pretty amazing. And then model it and figure out how it's changing over time. All right. So I'm going to skip this one really fast. If you want to watch it, it's pretty amazing. It's a big, huge ice sheet that breaks off in Antarctica. It's basically the size of Manhattan. And these folks were out there thinking something might break off a small piece because it's what it's known for, but then a chunk the size of Manhattan did. All right. So in order to get a little bit ahead so we can do some more things here, we'll skip that one for right now, but you can go back and watch it if you'd like. So here's some evidence now. If I told you, hey, there were areas in the United States and North America and stuff were covered by glaciers 15,000 years ago, how do we know that? What is the evidence? And so now I'm going to show you some of the evidence that helps us know where glaciers were. All right. And so one of the first ways to tell if there was a glacier there is what we call glacial polish. And you can see my foot there from like 13 years ago. But over granite and other rocks, as glaciers slide down the mountains on that base part, there's grit and rocks and things like that stuck in the bottom of the ice as it slides down. And so those rocks in the ice literally scrape and make those gouges, those striations, those lines, and they go in the same direction that the glacier goes, which is kind of cool. And what's really awesome, that paper I was mentioning that I read last week, there's new studies that show that, for the longest time, we've thought that the reason the rocks are kind of smooth and have this glacial polish, it's called, is they thought there was like fine grit, clay and sand, that if it's really small and fine enough, like fine sandpaper, it makes things really smooth. There's new research that shows that this layer of polish, that fine stuff, actually might be put on to the rocks and not scraped away. So as the things get scraped away, maybe some pieces of clay and other stuff get thinly layered on top, and that's what gives it that polish. But that's not even in any textbooks yet or anything. It's just brand new science. So be curious to see how that works. But for the most part, all you need to know is glaciers make scrapes in the rocks, right? If you got 1,000 feet of ice moving, that's a lot of weight and pressure putting on those rocks as they go over the top, and it can make these cool shapes. So like I was saying, that grinding, so if this was a valley right here, and this is a glacier and the flow's coming down this way, there's lots of grinding that happens down right over here. And also, as the glaciers move down, they pluck rocks off of the sides of the valleys, and that's how we'll see eventually they create those kind of U-shaped valleys a little bit later on. And so this was from 2 years ago when I was up in Yosemite. I should have taken out some of the blue in the photo. It looks really kind of blue, but that shiny polished area there, that's glacial polish. That's all smooth where the glacier went over the top. And then all these funky rocks right here, we'll give them a name in a minute, but these are called erratics. And all of these were trapped inside the ice or were riding on top of the ice of the glacier as the glacier was flowing down. And then as the glacier stopped flowing and started retreating and melting, the glaciers dropped out those big rocks that it was carrying right where they were. And so that's what you see in Yosemite. So if you ever see big rocks just sitting on top of smooth rocks, or big rocks sitting out in the middle of a valley far away from where a landslide could take it, it's probably a glacial erratic. So it hitched a ride like these chunks of rocks right over there in my picture that I poorly drew right here. They just kind of go along for the ride, kind of like at the supermarket when you go check out and boop, 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 on the conveyor belt thing. The rocks kind of ride it like a conveyor belt. And so it's kind of crazy. When I went to Hawaii in 2013, we ran into a friendly park ranger, and he told us that you're never going to believe what you're going to see up there, and showed us where to go. And sure enough, we went up to the top of Mauna Kea in Hawaii, and we found the glacial striations or the glacial gouging up on Mauna Kea, and glacial polish was much smoother. So during the little ice ages, there were glaciers on top of Hawaii, which is kind of crazy to think about, but it was so tall and so high in a cooler climate, it allowed glaciers to form. So who knew there were glaciers in Hawaii at one point? And so there's Mrs. H. Some of the other things, erosional evidence for glaciers. So this is erosional evidence, things that the glaciers took away. You can see more erratics over in the background, but more glacial polish, and these semicircles or like these half moon type things, those are called chatter marks. And so that happens when the glacier kind of goes and then stops and then goes and then stops. And it's like chattering along like that. And sometimes we'll break pieces of rock out. So this is another way to tell which way the rocks were, or the glaciers were traveling. So basically they're going downhill here. So kind of the front end of that circle is the end that got popped out. So it kind of points in the direction of the flow like that. All right, so that's erosional evidence of glaciers. There's also the U-shaped valleys that we're going to see some of the landscape features in a minute. But they also made some depositional evidence. So some evidence that showed that glaciers were there. And one of the really cool things that they've ever made are things called diamictites, or drop stones is another name of it. And basically, if you remember from the very first week or second week of our classes, we talked about snowball Earth on part of that Earth timeline that we did 700 million years ago or so. And that was the time when we think the Earth was basically frozen over, except for a thin band around the tropics. And the reason we think that, and here's the evidence now, is that as these glaciers that were on these different continents 700 million years ago, as they scraped rocks and things off, they got stuck in the ice, and when they broke off into icebergs into the ocean, these icebergs floated out into the warm tropical parts near the equator, and as they started melting, they would literally drop the pieces of rock that were stuck up inside of them and land in the soft muds of the seafloor. So what you see are these funny like river rocks and other jagged rocks and stuff that are just plopped right into the mud of the seafloor. And some of them, if they're really big, actually you can see like where they deformed and squished the layers of the sea mud when they hit, which is pretty amazing and pretty cool. And so if you go to Death Valley, that's of all the weird places, right? If you go to Death Valley, there's a big place where the formation of rocks where it's all made up of diamictites. And they're about 700 million years old. And what's really crazy for this is that what that tells us is this A used to be under the ocean. B, there were glaciers near the equator, because we know based on basically the magnetism within the rocks that this was near the equator at the time. So it was near the equator, it was under the ocean, and to have these drop stones here tell us that there were glaciers near the equator in the ocean 700 million years ago. And if you want to go see it yourself, you can go see all of these, which is pretty amazing. And there's rocks of the exact same age and the exact same type as this in Australia. So that's evidence that shows us the plate tectonic connection of, Southern California and Australia 700 million years ago were very likely in the same neck of the woods, which is pretty crazy and pretty cool to think about, I think, anyways. All right. And so there's the diamictites. That's the one thing that it can deposit. And then if you have these big boulders that look like they're kind of out of place, these are what we call the glacial erratics. And so these are the boulders that were carried and deposited by glaciers like a conveyor belt. And when those glaciers melted and stopped flowing, the glaciers melted, and then the big rocks that they were carrying just boop, sat down on the ground. And so in some places in the Sierra, it's really obvious because you have these big white granite boulders sitting next to like these metamorphic rocks. And you're like, well, how did that thing get here? The nearest granite's a mile away. Well, it hitched a ride on a glacier, and when the glacier melt, there it dropped. So it's pretty cool. All right. And notice there's also some glacial polish and glacial gouging and all that nice stuff. And here's another really, let me see here. And here's a really, really, really nice one of glacial erratics over by, it's called, oops, go ahead. This one is called, I can't think of the name of it right now. Not Pothole Dome. It'll come to me. McGee Lakes, no, Murphy Creek, that's one, Murphy Creek. And Polydome Lakes is the one I'm trying to think of there, Polydome Lakes. And there's all these amazing erratics with the glacial polish. That's so smooth. I mean, some of it's so smooth you could, if you had a pair of jeans that you didn't really care about, you could probably slide down and have some fun just on your keister. So, okay. So those were some of the evidences of glaciers, right? So we have the glacial gouging, we have the chatter marks, we have the glacial polish. We also saw then the depositional stuff, some of it. Those are a couple of the first types, right? So we can tie that information together to help us understand what we call these valley glaciers or these alpine glaciers and the cool things that they make, all right? So we're going to tie in some of these erosional and depositional features with these glaciers right here. So if you remember, we talked about rivers a few weeks ago. Rivers kind of make those nice V-shaped valleys where they kind of oversteepen the slopes and you have rock falls, and it makes those valleys that are fairly steep and look like the letter V. Well, it turns out that glaciers, they also like following those paths of least resistance very much like a river does. And so these glaciers, what will happen is over time, they will find river channels and they will start flowing down those river channels. They start accumulating, the glaciers start accumulating at that zone of accumulation up at the top of the mountain. They'll flow down those river valleys, and as they go down through there, they will basically start widening out those river valleys because the glaciers are heftier and they're plucking things from the side of the wall as they move down. And then eventually, once they get down to the end of the river valley or where it gets warm enough, they'll start to lose mass in that zone of ablation and start melting. And so this picture is from when I went to Athabasca Glacier on our honeymoon in 2000. Oh no, I should know what year I got married. 2006, I think. Yes, 2006. That's the year it was. And all these are cars down here, but this glacier has been retreating steadily. But what you can see is it used to be a river valley at one point, and then these glaciers have widened it out over time. All right. And so those glaciers will go down, pluck the rocks from the side. And because the walls or the glaciers, I should say, have enough pressure to push those walls, you can get steeper walls, and it grinds out those bottoms a little bit more smoothly than a river would. So you get this U-shaped valley instead of a V-shaped valley. All right. So these valley glaciers, right? These snowflakes, they get buried, they get compressed over time in the zone of accumulation, and they create things called ice. And if that ice starts flowing, that's where you get your glaciers. And this glacier is up in Juneau. If you ever have a chance to go to Juneau, Alaska, it's called the Mendenhall Glacier. It has also retreated very, very far in the last few decades. But on the left-hand side here, you can see they have this cool little exhibit within the visitor center at the Mendenhall Glacier there that shows how it starts as snowflakes. Those snowflakes then kind of melt and become firn, F-I-R-N, and then as it sticks together even harder, it creates that glacial ice way up high in that zone of accumulation. So you can't see where this glacier starts. Down here is a zone of ablation where it's basically going away. And so that's why I got you a Google Earth view. So here's kind of that equilibrium line, and this is where the glacier is forming. This is where the glacier is melting away, the zone of ablation. All right. And we already talked about the drills going down through there. So that basal slip flow is what you guys saw, was the glaciers kind of slipped and slide downhill due to gravity on its base. And it makes that plastic flow, like I already talked about earlier, how it kind of makes it move like silly putty. All right. So for us, right, many landscapes were changed by that widespread glaciers of the recent ice age. And it's something we see in California all the time. And if you ever get to go to the mountains, which I hope you get to at some point, you'll get to see some of these features on your own. And so one of the things we're going to do in a few minutes here is we're going to go on our own little Google Earth, and you guys are going to be able to add you guys are going to be able to add some of your own glacial stuff to there. So there's a couple of different things to look for here. Glacial landforms, that's what I'm trying to say, is there's U-shaped valleys and troughs. There's a thing called a cirque, a tarn, a horn, a ret, and a hanging valley. So these are the big 6 that you kind of need to see and know. And I'm going to show you lots of pretty pictures because they're really neat. So there's me when I was young, almost just graduated college on a geology trip. But these valley glaciers, they make that U shape. It almost looks like a half pipe. That's how you can tell one definite way that there's a glacier there, right? That's a U-shaped valley. And this was in Montana on the Bear Tooth Road. And he's an art professor, Dr. Saros at MJC, and he was one of the drivers on the trip. But he liked pointing at the U-shaped valleys that were out there. So anytime you see U-shaped valleys, those were carved out by glaciers, all right? And so we went there again a few, like 10 years later or so. And those are the U-shaped valleys. The same place, a little bit more snow there, but those U-shaped valleys were formed from grinding and plucking and that effect of that basal slip as it was going through. All right. So closer to home, here's a very good U-shaped valley up at, this is Kennedy Lake. So if you're familiar with Kennedy Meadows on Highway 108 or Sonora Pass, this is up on the backside of that, one of my favorite places in the world to go hiking. But there were glaciers there. How do we know? Big honking U-shaped valley right there. All right. And it doesn't always necessarily look like a perfect U, but it looks very much like a half pipe. All right. This is on the side of Mount Rainier in Washington when I was there 11 or 12 years ago. But you can see it's a small U-shaped right here. And this was a glacial valley and is. And here's the funny thing. The reason the bridge is built right here for the road that goes around Mount Rainier is because in the 30s when they built it, the glacier was right here where the bridge was, and they wanted people to drive and pull over and stop and see the glacier. But you can see the glacier is no longer there. It has retreated upstream quite a bit. So now let me ask you this. Here's Yosemite. Does this necessarily look like a U shape? I mean, people see this side, they see this side. It's kind of hard to make out the classic U's like I was just showing you. And so the thing I want you to think about and imagine is next time you go to Yosemite Valley is you're literally standing on some places over 1,000, in some places maybe even 2,000 feet of sediment, of dirt and sediment that's been piled up over time. So there is a nice U-shaped valley at the bottom there, but it's been filled up with sediment, and that's what makes the flat Yosemite Valley that everybody goes and hangs out at these days. All right. So those are U-shaped valleys. We have other ones that are well, I like them all. If you don't know, glaciers are just my favorite thing to go see, or glacial landscapes anyways. These are called cirques. And so cirques are the big bowl. It's like a bowl-shaped depression carved at the head of the glacier. So this is where the glacier started and kind of gouged out this big bowl-shaped area. And then as it moved downstream, that's where it started carving the U-shaped valley. So if you go upstream from U-shaped valley, this is where the glaciers started. The lakes themselves that usually happen that you see there, they have a special name. This is called a tarn. And so this is a lake in a glacially carved cirque. So a tarn is just a glacial lake, basically. And these two pictures are the exact same place. This was in July of like 2004. This one was just 2 or 3 years ago in July as well, when we had that heavy snow year, and the snow hadn't melted yet. But you can kind of imagine what a glacier might have looked like there when it was there. So, oh yeah, 2007, 2012, 2018. So all the same place, different times, basically the same months, but just different amounts of snow on each year. Gorgeous places. Big fish, if you like big golden trout there too. All right. Here's a Google Earth view of a cirque in Mount Whitney. So there's a cirque and there's a tarn. And that's what it looks like if you actually get to go camping there, which I did a few years ago. It's an amazing place. So this is the head of a big glacier at one point, and it carved out a little bit more of a depression there, and that's why there's a lake. So there's our tarn. The cirque is the stuff in the background. So there's more tarns. All right. And then we have horns. Horns are kind of a cool one. They're basically kind of like these pyramid shaped peaks, and they're created when you have a bunch of back-to-back-to-back glaciers. This is an old picture from one of my first pictures of glacial stuff back in 2002. Here's another pilot peak. So anytime you see these kind of weird alpine Matterhorn peaky looking things like this, the Matterhorn in Switzerland, that was created when you had a bunch of glaciers back to back to back to back to back. And I'll show you a picture of them in Google Earth that explains it a little bit better in just a few minutes here. But basically, you had a glacier going off this way and a glacier going off that way and another glacier on the other side. And as they all went their own separate directions and wore the rock away, it just left behind this point. All right, so that's called a horn. Arêtes are these kind of sharp, jaggedy ridges. And basically, these sharp, jaggedy ridges like this, that's called an arête. It's where you had racing glaciers on either side. So glacier going this way, glacier going that way, making that U-shaped valley. And then that point in the middle, that's your arête. All right, so arêtes. And actually, you could probably call this a horn right here if you wanted to. So again, glacially carved landscapes are just some of the most beautiful things to go hike in if you ever get that chance and opportunity. And you can see them also up in the Sierras. So this is when I hiked on Mount Whitney. There's a horn, there's our arêtes. So U-shaped valley going down. All right. So the last couple ones here are called hanging valleys. And so these hanging valleys are pretty cool. If you go to Bridal Veil Falls in Yosemite, this is what Bridal Veil Falls is. And it's created when you had glaciers, small glaciers intersecting with a big glacier. So the small glaciers couldn't really cut down as deep because they kept smashing into the big glacier as it was going downstream. And so what happened is after the main glaciers melted away, you get these valleys that look like they're just hanging, and that's where it creates your waterfall. So anytime you see waterfalls in Yosemite, you can pretty much guarantee you're either standing on the edges of a glacial U-shaped valley or a hanging valley like this. And so, oops, there we go. So imagine this is what Yosemite looked like 12,000 or let's say 18,000 years ago or so, something like this. I just kind of drew this in. I'm sure you can't tell I drew this, right? But here's El Capitan, Half Dome would be over there. That's about this is the height of where the glaciers would have been during the last ice age. And then here's where Bridal Veil Falls is, that valley. And that's what that small glacier in Bridal Veil Falls would have looked like. And now it's melted, you get the hanging valley. So you notice it's a U-shaped valley and then it just ends, it's hanging, left it hanging. That's why it's called a hanging valley. Glacier National Park has lots of them. All right. So, oops, let me see here, sorry. So the last little bit here, is called a moraine. And this is a glacial deposit, one I didn't show you earlier because I didn't want to like blow the surprise. But the blue dots that my wife is standing in front of in Yosemite Valley here, this is a moraine, which is basically, it's the debris that's been plucked and transported and piled up by glaciers at the end of a glacier. So when we did, oops, let me see if I have that simulation up still. Let me go back there. Up, it's still growing. Some of you guys noticed there were like these black dots that were in the glaciers that would pile up over time. Those are supposed to represent the rocks. And when the glacier keeps advancing and flowing like that, you don't really get that pile up. Let me see if I can get that pile up to go. There we go. So now it's retreating and you see how it's kind of dumping off these piles. If you can imagine a glacier, if we could get it to stay here for multiple years, how those piles of rocks would just start building up at the edge. That's what a moraine is. All right. So it's all the stuff that was plucked and transported and left behind. It's very much like the conveyor belt at a grocery store. So some people get the idea that it bulldozes through and like bulldozes stuff like a bulldozer does. That's not what happens. It actually is transported more like a conveyor belt and then gets dumped at the end of the conveyor belt and builds up. So the bigger and taller the moraine means the longer the glacier was there dumping stuff in that spot. All right, for the most part. And so Convict Lake, if you ever go to the eastern side of the Sierras, there's really amazing, beautiful glaciers here. But all of these funny hills that you see right there, those are what we call terminal moraines, or they're the moraine from the end of a glacier. We also have what we call lateral moraines, which are the piles of dirt that were deposited on the sides of the glacier as it retreated going back. So that's why it's called a lateral moraine. And you wouldn't even notice it. Sometimes you're just driving down the highway. You're like, oh, wow, there's this big pile of loose jumbled rock over there. Oh, Danielle, sorry, go ahead.
How do you know if it's a moraine or just a hill?
That's a great question. And that's something that you guys are going to be looking at in just a minute here. All right. Great job. Great question. And so that leads me to this. I was like, you're reading my mind. All right. So how can you tell if it's a moraine or glacial deposits or just a hill? And I'll show you some other views and vantage points in just a minute. But first, we're going to do a quick little breakout because I've been talking forever and I apologize, but I get excited about glaciers. So here we go. Copy link. I think that'll go there. So here's the next Jamboard. So this one's only a 5-minute. It's not long or anything like that. All right. But basically, you're going to get into your little Jamboards groups. Hopefully this will load up for you. And you're going to have 2 pictures. They're both in Yosemite, taken on the same day when it's icy and cold. The Merced River is on the right at sunset, so that's why it kind of looks orange. This is Tenaya Creek on the left-hand side. All right, so what I want you to do is just kind of look at these, what are similar and what are different. So these are glacial deposits on the left, river deposits on the right. What are some things that are similar? What are some things that are different? Just come up with as many things that you notice and wonder, and we'll go from there. So 5 minutes at the most, breakout room, it's pretty easy, and just see who can get the most stuff, who can get the most ideas. And let me get you into your breakout rooms. And on your marks, let me change this to, I'll go 4 minutes. That'll probably be plenty of time. And here we go. All right. Oops, let me see. Jennifer, were you in a group before?
No, I had mentioned that I was going to go get my vaccine.
Yeah,
but I
that's
just
totally
got
fine.
back.
That's fine. Let me get you to a group here. And Marina or Mariana, were you in a different group already or no?
I was in group 2.
Okay, I'll put you there then. All right, and so Jennifer, I will put you in room 3. All right. So great job. I think you guys pretty much nailed it on the head for most of what I saw here. And it's that the big idea is the rocks and the rivers are rounded, and then the rocks and the piles of rocks over on the left-hand side in the glacier deposits, they're more angular, right? And so that could happen in a rock fall, perhaps, right? You can get rock falls that break up and get different sizes of rocks, but usually what happens in rock falls is you don't have the really like fine clay and other stuff that supports it. So the one way that helps us really understand that this is glacial deposits, or what we call glacial till, is that you have these big chunks of rock mixed in unsorted with small sizes of granite or gravel and sand and clay and things like that. Because in rivers, remember we talked about how when rivers turn around the edges, they deposit sand and gravel in some places and they erode on the other places, and then they carry their fine sediments all the way out to like deltas. It sorts and separates out those different size particles over time. With glaciers, that's not what happens. With glaciers, it just carries everything at once and dumps it. And I think I got my PhET simulator working here a little bit so that it's in the same area, just continuously dumping stuff in the same area, building like this wall of rocks, if you will. So this is how moraines get started. So to answer Danielle's question earlier, how do you know if it's a pile of, if it's glacial deposits or glacial moraines? That's the big way to tell, is if you see angular rounded or angular rocks like this with a bunch of other mixed up stuff in it, it's usually going to be, so angular rocks, big and small angular rocks all together, and sand and grit and stuff like that, that's going to be glacial deposits. Whereas if you see old riverbeds, those are all going to be generally rounded. They're going to be more sorted. You're going to see a lot more similar sized rocks all together. And the other thing to know is just if you're in an area where there's like U-shaped valleys, that's a pretty good way to tell too. So if you've ever driven to Yosemite, the east side of Yosemite, here's Mono Lake. By the way, Tioga Pass, the road that gets over this, we're getting some snow this weekend, but I would pretty much guarantee that this road is going to be open and plowed of snow by the first week of May, maybe the second week of May, which is going to be pretty early opening. So if you want, you can drive over there in May. But what you're seeing here in Lee Vining, just outside of the little town of Lee Vining, all of this, A, you see a U-shaped valley, and B, these are all lateral moraines, or moraines from the side of the glacier. And if you go hike these hills, they're all piled up jumbles of rock that were left there by the glaciers as it went through. And what's pretty cool, well, not pretty cool, but what's really awesome is you'll notice there's a really tall one, and then there's a smaller one, and then there's a smaller one. These all represent 3 different periods of glaciation. And so this is a really cool thing that we can do as geologists and geoscientists, is we can actually map and figure out when the glaciers came through. There's ways of dating rocks now to figure out exactly how old some of these piles of rocks are, which is pretty cool and amazing. But we can see that there have been at least 3 glaciers popping down this valley in the last, well, in this case, 100 and some thousand years or so, pushing down into here, which is pretty cool and pretty slick. And let me see if I can find a good street view here. Oh, so as these glaciers melt, all right, as these glaciers melt, imagine there's a glacier all the way down here, and it's slowly melting and it's retreating back up the valley, just like your simulators go. It leaves what we call not the big, huge pile of the terminal moraine at the end, but it leaves little piles along the way. And those little piles are called recessional moraines. You don't have to know this, but in case you really want to care and see what it looks like, these recessional moraines are the big piles of moraine that you can drive by. And so most people would just drive by, they're in the valley right here, and they're like, oh, here's a little bump in the road. Well, it turns out that bump in the road is a moraine. And that's where the glacier, as it was retreating, kind of paused and stayed there maybe for 5-10 years. I don't know how long it took to build that up, but it's just a few years. And then it started retreating again. And as it started retreating, built another one of those. So let me ask you this, what would happen if glaciers started forming again and started pushing down this valley? Would this evidence of glaciation, would these recessional moraines still be here? Or what would happen to them if a new glacier starts pushing down? It's going to wash them away. It's going to bulldoze them, well, not bulldoze them, but it's going to go over the top and it's going to carry that debris and push it down at its new terminal moraine down there. So yeah, they just be annihilated and flattened. And so when you're driving down this part, it's pretty amazing to think like, dude, this whole thing is one big U-shaped valley. There's recessional moraines and all this hill off to the side. That hill is nothing but one big tall, we call a lateral moraine, or moraine on the side of the mountain, or the side of the valley, I should say. So, and there's lateral moraines there. There's another lateral moraine right here, and another one right here, and another one right here. And here's the one thing I really want to just show you that just blows my mind. All right, so here's all the glaciers coming in, or the U-shaped valley coming into Mono Lake. Here's some more U-shaped valleys coming off of Sonora Pass, or near Sonora Pass over here. You can see the lateral moraines. You can see a terminal moraine, and part of that moraine is gone because the river cut through and eroded it away. But a lot of this is all glacial deposit out here. And if I zoom out just a little bit, I'm going to zoom out so you can see all of Mono Lake. During the ice ages, this whole area that you see right here, these are old shorelines of Mono Lake. And all of this was Mono Lake at one time during the ice ages when it was cooler and wetter and there wasn't as much evaporation in the desert. So what's kind of cool is that shoreline you can see is our flat areas out here in Lee Vining, right here and right here where the gas station is and a few other little houses and stuff are. During the ice age, Mono Lake would have been right here, and those glaciers would have been flowing right into Mono Lake and breaking off, making icebergs flowing out into there. So the next time you go to Yosemite, if you ever go to Mono Lake on the east side, which I highly recommend, it's amazing and beautiful, just think about, man, there's a glacier right here pumping out icebergs floating around across this big, huge lake out in the middle of the Eastern Sierra, right? It's just, for me, it's mind-blowing to think about. And it's so cool, but that's just me. I guess maybe I'm a nerd, but if I can at least impress upon you to go check it out sometime, I highly recommend it. And so you can see in this moraine, we go back to here, there's big boulders, there's small boulders. Sometimes you can get rounded boulders in there because maybe they had been in a river as the glacier went down, but for the most part, they're jumbled. They're not really well-rounded, and they have that mixture of sizes of stuff. So some of the evidence that we have that the whole entire North America was under glaciers a long time ago is, well, we have big, huge terminal moraines from a huge continental ice sheet that stretched from like Boston all the way to Long Island. And these are all moraines right there, which is pretty cool. In Yosemite, the park geologist, Greg Stock, he's an amazing person, and he has gone and basically hiked all around Yosemite and has found the evidence and looked at the glacial striations and looked at the glacial polish to figure out how tall the tallest glaciers were and how far they flowed during the last glacial maximum, or the biggest ice age that we've had. And he was able to put together this amazing map, and I think it will load if you just give me one quick second. So Danielle, while it's loading, go ahead.
So I have a question. I always kind of assumed like where there's roads and stuff that the hills and stuff around it were like man-made, like as a result from like clearing out for the road. Is that not true most of the time? Is most of that
like in Yosemite or any specific points, or just in general?
Just in general.
Yeah, in general, I would, if they have road cuts and things like that, I would probably, I mean, it's not going to be glaciated. Like in the Central Valley and Turlock or anything like that, it's not going to be glaciers. And for a lot of that, that would be just like construction debris and stuff, that they have to scrape out and put somewhere.
Okay.
The thing I can think of the most that's popping into my mind is like where the aqueducts are in California. Like if you go by Patterson, you have the big canals, concrete canals, and then on the sides are these big mounds of dirt. Well, that's the dirt they dug out to make the canal, that they just piled up on the side because they didn't want to spend money to ship it off to someplace. So yeah, for the most part, if you're going to a place where it was likely there were glaciers at one point, like in the high Sierras or Yosemite or Montana or places like that, then yes, usually the roads are going through areas that have probably been glaciated because that made a nice path that we could now make a road or drive on and hike through and things like that.
Yeah, I'm thinking of like Upper Tuolumne and Calaveras counties and stuff.
Yeah, it did well in Tuolumne for sure, and in some parts of Calaveras County, you might be getting into a little bit of the areas where it was glaciated, but for the most part, it's probably just rivers and road cuts and things like that are human made. Yeah, and so thank you for that question. And here's that map if you want to download it. It's a massive map to download, but it basically shows where the glaciers were and how they started flowing. And you can see in Yosemite Valley where they started popping down into, but it was all the way up at Sonora Pass, even for a little bit further north, but this one just happens to look at all the glaciers in Yosemite. This was, I think, about 18,000 years ago at the last maximum. What do they say on the bottom? And you can see my computer is hefty and it's a big file to download. The last glacial maximum, so I think this is about 18 or 20,000 years ago, somewhere in that neck of the woods. All right. And they can use all the evidence that we just talked about and have looked at, the erratics and the moraines and the glacial polish and things like that to figure out what it looked like. So what did it look like? They're building a new visitor center in Yosemite starting this summer, but in the old one, you can find these pictures. Basically 50 million years ago, this was Yosemite, kind of a lowlands, hilly area, but kind of lowland area in terms of what the high Sierras are today. And there was about 40 million years worth of erosion. No glaciers, just rain. It was more tropical climates at that time. We find fossils in the areas around Ione and Calaveras County and places like that. We find tropical ferns and things like that. So that's about 10 million years ago. And by about 3 million years ago, the uplift of the Sierra starts happening, which causes steeper gradients. The rivers start downcutting much more quickly. And so you start getting the erosion. And maybe this is starting to look familiar. The ancestral Merced River probably carving down there. I wonder what this is going to be. And so then about 1 million years ago to 250,000 years ago, we had our first really big ice age that's really recorded well in a lot, I wouldn't say first, but one of the ice ages that's really recorded well in Yosemite Valley. And during that maximum, there's glacial polish all the way up near the tip of Half Dome and on Clouds Rest and El Capitan. And that's how we can figure out how high those glaciers got. By about 30,000 years ago, they've retreated. There's still lots of glaciers and things in there, but it's retreated quite a bit. I don't think there was any Twitter back then. And then by about 10,000 years ago, the moraine at the end of the Yosemite Valley Glacier made a dam. So that picture where you saw my wife standing earlier, that used to be a moraine that backed up a lake, which made a lake in Yosemite Valley. And there's cool lake fossils and stuff that you can find underneath some of those if you go down a little bit deep enough. There's a few little bits preserved, but it made the lake and the sediments that we all live on, or the places that we drive around in Yosemite today, 10,000 years ago, was at the bottom of the lake. And so that's kind of how we got modern Yosemite Valley. That's how it was carved out. Here's a honeymoon pic from 2006 in Canada. So switching from Yosemite back to Canada, but there's some arêtes and amazing U-shaped valleys. But this one went through sedimentary rocks. And so those sedimentary rocks and metamorphic rocks that are there, they were uplifted. They're softer than the granites and they get carved out a little bit more easily. That's the Athabasca Glacier I was showing you earlier. And what's kind of cool about this and sad at the same time is they have a trail and a path. Once you park, you can go see where the glacier was at different decades. So here's 1982, here's 1992, and you can see where it's retreated. The good thing about that is you can actually see, if you look at those rocks, you can see the glacial scouring and the polish and the glacial gouging on there. So it's evidence to show us that yes, glaciers did make those parallel scrapes on that mark. And we see more and more of it as the glaciers retreat up the hill. All right. So I just want to end with a few, well, end this part anyways, showing you how things have changed a little bit. So this is Glacier National Park, Iceberg Glacier. This is what it was in 1940. And here's what it looked like in 2008. And I guarantee you it's even less than this now. All right, so went from that to this. And here's the Boulder Glacier in Glacier National Park back in 1913. And here's what it looks like in 2012, so about 10 years ago. This is from the USGS. So you can just see how much the glaciers have gone. And we'll figure out why that is in a little bit. But now for our last thing that I'm going to do, I'm going to give you a link to this Google Earth file in just a moment here. Don't open it yet. All right. But what's going to happen, and let me move my face so I can navigate myself here. Where'd I go? Oh, glacier identification. Here it is. So this is meant to be a little bit of practice for your final project as well. Not that you have to put anything in this for your final project, but I want everybody to zoom in to one of these areas. So you'll see on Google Earth here, I have a couple of areas that are highlighted in blue. There are also, there's one big area in what is that, yellow or orange or something like that over there. And the reason that's there is because, remember we talked about the moraines being all the way up through Long Island and places like that. The Great Lakes, are actually glacially scoured land. So the glaciers scraped out softer rock where the Great Lakes are. And then as the glaciers retreated, the Great Lakes filled up with water. So I guess you could maybe call these big giant tarns, but that's why that yellow box is there. But what I want you to do is you'll navigate and you'll kind of fly around in Google Earth like you've done. Everybody's going to do their own. So I'm not going to put you into breakout rooms. All right. Everybody's going to do in their own. And basically anywhere within this box that you see, you're going to be able to find good examples of glacial evidence. All right. So you can find glacial evidence in each of these areas. And if you click on the thing over on the side, it'll tell you this. So you just zoom in. You can use your scroll wheel to zoom in or to zoom out. If you press, I'm having a hard time tonight, push or press the shift key, it'll help you go 3D and move around like this. All right. If you press the Alt key, and I'm not sure what it is on Mac, but if you press the Alt key, it just lets you drag it around. And if you press the Control key, it's like kind of looking around. So like you're staying in the same spot, but just looking around in 360 degrees. Otherwise, you can just drag it and drop it. So here's what I want you to do. I want you to find, so remember we have arêtes, we have tarns, we have cirques, the bowl-shaped areas, things like that. I want you to drop a pin on a glacial feature. So for example, right here, I've already dropped a glacial tarn pin. The way you drop a pin is if you go down to the bottom part where it says add a place mark, you can just click a place mark and that's highlighted. And then you just go to the map, go anywhere you want on Google Earth that you want to drop that. I'm going to put it right here and I'm going to say, oh, this is a tarn. And so I'm going to save that. Or actually, before I do that, I'm going to edit the place. So when you do this, when it says edit place, basically it has the title. All I need you to do is put your name right in there. So for me, just put in Hollister. And this is it's a typing box, just like you have in normal web editors or Canvas or whatever. And that's going to be kind of the pin that you drop. And when people click on it, this is the thing that's going to be displayed. If you want, you can change different icons down in the bottom left-hand side right here. So I don't know, I just want it to look like that. So I'm going to make it look like that. And then when you're done, you just click the back arrow and it's been added down at the bottom right here. And so what's kind of cool now is if you click on that, it pops up an information box that says, hey, that's a tarn and your name is on it. And I'll show you later on in the tutorial of how to add pictures and things like that, but we don't need to. If you want to get really advanced for this, if you want to say like, oh, hey, this whole thing is a circ, like maybe right over here. Oh, that's a circ. You can also add lines where you just click and make a little polygon. And once you click, you finish it off at the end, you can say, oh, this is a tarn in a circ. All right, it's tarn in a circ. And then you would edit place, type in your name, and you add it to there, and it's on the map. All right, so basically by the time we're done with this, I would like everybody to add 1 or 2 different things. You can go and click and add moraines. You can go and click and add a lot of different things. So there's stuff in the Central Sierra or the Sierra Nevada. There's also, if you just want to know how to get there, if you click on one of these up here, there's the Sierra. Here's Glacial National Park and up in the Canadian Rockies. This has amazing glacial landscapes and features that you might want to just get lost in and zoom in and take a look at. And if you drag the Street View person, you can find little 360 images, right, to drop yourself into. Ooh, let's see, where are we going, right? And you can add something there, or there is also some up in Alaska as well. And I don't know why it's not dropping me in here, but let's see. Oh, come on, go. Go, 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 go. You never know what you're going to get. It might be high quality. It might be not so great. Ooh, there we go. Ah, look at that. Don't you want to be in Montana right now and go see that? That's pretty awesome. And I bet you $1 there's some fossils in these areas as well. But holy moly, look at those tilted rocks and strata, just amazing stuff, folded and crushed. So that's all I need to do. And so we'll add some of that stuff on there, and then we'll take about 5 or 6 minutes to do this. And then once we do that, I'll have a little closing and then we'll be done just a little bit early. All right, so let me give you the link to this. It is right back here. That's the one thing I hate about Canvas is it pops those links and makes it impossible. Let's see, there we go. Canvas isn't too terrible. It's not as terrible as some of the other ones I've ever used. Oh man, where's that? There it is. All right. Oh, there we go. All right, so I think that should click you and get you onto Google Earth here. And once you're on, you can add. So remember, we have moraines and tarns and other things like that. And maybe I should, that's what I'll put up here for my face, is you guys can see all those examples here in one spot. Where are we going? There we go. And you already know what erratics and things look like, but I don't think you'll be able to find too many erratics in Google Earth unless you go into a Street View or something like that, which you might be able to. So plug away, go onto Google Earth there, find 1 or 2 things, add yourself on there, and we'll come back in like 4 or 5 minutes. And if you need help of how to add a button or drop a button or something, let me know. This is like the 101 class, and I'll give you a few more advanced tips and tricks in the video that shows you how to do the final project. So yeah, you can just zoom in and I mean, just find a spot anywhere. Wow, that's pretty. Oh yeah, if you need help at the I forgot to put in the title slide. So of this Google Earth slideshow, if you go to the very top where it says Glacial Landform ID, you click on that, it'll kind of give you some ideas if you don't remember. So let me see, I'm gonna reload this. And I think if I reload it, maybe that's when everybody else's changes start showing up. Yeah, all right. You guys are starting to get it. Good job. Let's take another 3 or 4 minutes, just get one on there. You don't have to do them all, but if you want, you can go in there and do more. I'll never prevent you from doing more. This is one of my boring hobbies. If I get bored at night, I go in and I just play around in Google Earth, and I like imagining trying to go hiking different places. In fact, I'll show you my dream hike in the next few. I don't know if I'll do it this year, but let's see. Right near Mono Lake is Burrow Lake. Look at that. Nice little tarn right at the cirque, but the only way to get there is you have to crawl up this huge, massive canyon. And that's really rocky and steep. But look how beautiful it is. Burrow Lake. I'll have to get there someday.
What are the ones called on the sides that?
Oh, the lateral moraines?
Yes, thank you.
Yeah, yeah. So while you guys are doing this too, like all of, if you're up by the Sonora Pass area, anywhere where you see the granite really exposed, not even Sonora Pass, but by Pinecrest, that was all glaciated. Pinecrest sits in a glaciated valley. There's glacial erratics around the hillsides scattered around Pinecrest. And if you go up into like any of the valleys behind Cleo's Bath and stuff like that, you can see that it's a very broad, glacially carved U-shaped valley. So lots of evidence of glaciers in the Emigrant Wilderness and everything up by Pinecrest for those folks that like hanging out in that neck of the woods. Dodge Ridge, part of it, skis down the U-shaped valley, which is pretty cool. All right, let me try this. All right, let's do one more minute here, and if you know you need extra help with if you need extra help, then that's totally fine. I just doggone it. I went away from my file here. But Google Earth is just such a cool, powerful tool for oh, you guys are awesome. Look at that. Good job, everybody. So I just had to reload it and you guys are popping stuff on there. Ooh. Yes, great. All right. So you've got it on there. I forgot, I need to show you one last feature in Google Earth. And it's not anything that you can get on where we're at right now, but if you Google Earth time lapse, don't go to the time lapse Earth engine. We need to go down to the new one, which is time lapse in Google Earth. And this is pretty amazing. They've taken all 30, almost 40 years of Landsat imagery. So satellites that go orbit around the Earth, gathering information and pictures. they've taken all 40 years and they've been able to make time lapses of different spots. And so one that I think is really interesting is if you go up into some of these areas in Alaska, like this is Columbia Glacier. It's Google Earth still, but give it a second. Once it's there, give it a second to load and let my face move away. It's still loading. So it's going to take it a few minutes here, maybe not a few minutes, but a few seconds. Give it a second to come in and get resolved. All right, so there's what it looked like kind of in 2020. Here we go. So we started in 1984, and then 86, 87, 88, 90, 91. But watch what starts happening to the Columbia Glacier right around 2000. Boom. By the year 2000, it's gone and it's retreated all the way up to these arms. So in the last 40 years, we have all these satellite evidence to show how these glaciers have retreated. And you can go anywhere on Earth and do these satellite time lapses, which is just amazing. So like if you go down to outside of Oakdale and stuff like that in Turlock, so check this out. Let me see here. This might be something to work at. Oh, come on. Pause. There we go. Let me find Turlock. Should be right around here. I don't know why my internet's going slow or something. But if you give it time to resolve, what's kind of cool is you can see how different lakes have fluctuated over time. It gets higher resolution than this. It's just not there yet. But you can also see how cities have grown and how some areas and land have been converted to agriculture. Like look at right up here by Oakdale, right? This is all rangeland, and in the last 20 years or so, it's basically been converted to almonds. Look at this. There you go. So pretty crazy. So that's just one other thing I wanted to show you can do with Google Earth before we left, and I almost forgot to show that to you. So we're done for tonight, basically. Yay, good job. Now, the last thing I want to show you here is, remember, here's our sketch notes. And then two pieces of advice, or not advice, but two things to leave you with for next week here, all right? And that's this. We're going to be talking about weather and climate starting next week. And I just want you to know right off the bat that weather is short-term. All right, temperature, humidity, wind speed, cloud cover, things. It's what's happening outside today or this week. That's what the weather is. All right, that's what your weather stations measure. Climate is kind of the general pattern of the atmospheric conditions over a long period of time, you know, for a region's specific time of the year. So in Turlock, you know, what would you expect it to be like in July? Or in Yosemite, what would you expect it to be like in June or January, depending on where you're at, all right? And so it's a long-term average of those weathery days that happen at any given time, all right? And so one of the famous quotes is, climate is what you expect, weather is what you get. And that's what we're going to be looking at next week. We're going to be starting to talk about what controls the weather and what controls the climate. We're going to leave kind of the geosphere and start going into the atmosphere and looking at the different climates in different regions. All right. So we're going to be looking at these climate graphs and cool things like that. But all I really need you to do for next week, as we start talking about these averages here, what I need you to do for next week is just make sure that you're bringing in like a 2-liter bottle or a soda bottle or anything that you can, a small piece of paper that you can roll up into like the size of a pea or so, and then a couple of textbooks that you can lay a piece of paper on. And we're going to do some experiments with air so that we can do some fun stuff next week. Other than that, I think that's pretty much what I got for tonight. We'll get done a little early since we went a little long last week. I'll put up another little quick tutorial video for Google Earth to show you how to do that for your final project. And that's where we'll go for tonight. And hopefully I can inspire you to go see some of these amazing places someday. Yosemite, you'll need a permit to get in starting at the end of May, just so you know. I think maybe I said that at the beginning of class, but and it might be a little crazy. I think I might be braving it to go to Yosemite tomorrow, but I have some photographic interests in mind. Sunday is not a good day to go to the mountains. It's going to be snowing really pretty bad on Sunday. So don't go to the mountains there if you're not comfortable with snow driving. Other than that, we'll call it quits. That's glaciers. I hope you get to see one before they melt. And Hope you have a good night. Let me give you your sunshines and blues, and then I shall send you on your way. Maybe. There we go. Sunshines and blues. And I think it's the right link. I think last week I gave everybody the wrong link and nobody said anything. Oh my gosh. There we go. All right. Sunshines and blues. And then hope you all have a really good evening and a good weekend, and enjoy the rain and get everything done that you're hoping to get done on your list, or some of the things anyways.
Have a good weekend.
Thank you. Bye.